Germany, Hambach mine. Present day. You're standing in an open pit coal mine watching something that shouldn't exist. A machine, 96 meters tall, 225 meters long, weighing 14,200 tons, moving across the landscape like a mechanical cathedral consuming earth. This is BAGGER 293, holding the title of the largest land vehicle ever built by humans in the world. We see massive excavators on construction sites almost every day. But next to this machine, those machines look like toys. BAGGER 293 doesn't dig holes. It literally removes mountains. It doesn't load trucks. It processes 240,000 cubic meters of earth every single day. That's enough material to fill 96 Olympic swimming pools. But here's what nobody tells you about this machine. It's not just big. It's an engineering compromise that almost killed its own operators. It's a mechanical monster that cost more to fix than to build. And it represents a dying industry desperately clinging to relevance through sheer scale. This is how BAGGER 293 really works, and why machines like it will never be built again. The story of BAGGER 293 begins with a problem that sounds simple. Germany needed coal, lots of it, and fast. In 1995, German energy company RWE was operating the Hambach mine in North Rhine-Westphalia. The mine was producing 40 million tons of lignite coal annually. Lignite is low-grade coal, burns dirty, low energy content. But Germany had massive deposits buried under 200-400 meters of overburden, the dirt and rock sitting on top of the coal. Traditional excavators couldn't keep up. Too slow, too small, too expensive to operate in sufficient numbers. RWE's engineers calculated they needed something that could remove 240,000 cubic meters daily. That's 320,000 tons of earth per day, every day, for decades. The solution seemed absurd. Build the largest excavator ever conceived, not 10% larger than existing machines, not even twice as large, 5 times larger than anything previously built. The project was assigned to Tackruf, a German heavy equipment manufacturer with experience building massive mining equipment for East Germany during the Cold War. But even Tackruf had never attempted anything at this scale. The first prototype designs were rejected. The machine would be too heavy, it would sink into the ground, the structural stresses would tear it apart. The power requirements were at impossible levels, but RWE was desperate. They authorized the project anyway. Budget 100 million Deutsche Marks, approximately 60 million USD in 1995. What they got was a machine that redefined the limits of engineering and exposed those limits catastrophically. The monster's autonomy. BAGGER 293 isn't just one machine. It's a mobile factory consisting of 11 major systems working in precise coordination. The dimensions are genuinely very difficult to comprehend. Height, 96 meters, 315 feet, taller than the Statue of Liberty. Length, 25 meters, 738 feet, longer than 2 football fields. Weight, 14,200 tons, equivalent to 2,000 full-size SUVs. Bucket wheel diameter, 21.6 meters, 71 feet, a spinning 7-story building. Power consumption, 16.56 megawatts, enough to power 17,000 homes. But here's what makes it actually work. The machine sits on 12 crawler tracks. Each track is 3.8 meters wide. The tracks don't carry the full weight evenly. The machine uses a sophisticated weight distribution system that shifts load dynamically as it operates. Why? Because BAGGER 293 moves across ground that's already been excavated. Soft earth, unstable terrain. Without dynamic weight distribution, the machine would sink through the ground like a ship through water. At the front, the bucket wheel, the massive rotating excavator, consists of 18 buckets. Each bucket holds 6.6 cubic meters of material. That's enough to fill a standard dump truck bed. The wheel rotates at 0.3 RPM. Sounds slow? It's not. The outer edge of the wheel is moving at 10 meters per second. That's 36 kilometers per hour. When a bucket filled with 15 tons of earth is moving at that speed and hits rock, the impact force feels equivalent to a car crash. The excavated material doesn't fall to the ground. It's immediately transferred to a series of conveyor belt systems, 7 separate belt systems running through the machine's body. Total belt length, 6,800 meters. The belts transport material at 4 meters per second, delivering it to discharge points up to 300 meters away from the excavation face. This is where the engineering gets truly insane. The conveyor system processes 240,000 cubic meters daily. That means 166 cubic meters per minute, 2.7 cubic meters per second, constantly, for 20+ hours per day. The power system is equally absurd.
Bagger 293 doesn't run on diesel. It can't. The fuel requirements would be unmanageable. Instead, it's powered by external electricity delivered through a trailing cable system. The cable is 6.6 inches in diameter and carries 30,000 volts. The machine requires 16.56 megawatts continuously. To put that in perspective, a modern aircraft carrier uses about 200 megawatts. Bagger 293 uses 8% of an aircraft carrier's power, a single excavator consuming as much electricity as a small town. Nightmare scenario. On March 17, 2001, something went catastrophically wrong. Bagger 293 was operating normally in the Hambach mine. The bucket wheel was rotating, the conveyors were running, the scheduled 240,000 cubic meters. Then the ground gave way, not all at once, gradually. The forward crawler tracks began sinking into soft earth that geological surveys had missed. The machine's front section dropped 2.8 meters inward in approximately 90 seconds. The operators felt it immediately. The entire superstructure tilted forward. Warning alarms screamed. The automatic shutdown systems activated. But here's the nightmare. You can't just stop a 14,200-ton machine that's actively sinking. The momentum is too great. The weight is too distributed. The systems are too interconnected. The bucket wheel, now angled downward at 12 degrees, struck bedrock it wasn't supposed to reach. 3 buckets shattered. 45 tons of metal fragments scattered across the excavation face. The impact shock traveled through the boom structure, cracking welds that had been certified for 40 years of operation. The conveyor belts, suddenly running at wrong angles, began spilling materials. 600 cubic meters of earth and rock poured into the machine's internal structure. Motors overheated, trying to move material uphill at the new angles. The external power cable, under sudden tension as the machine shifted, pulled free from its connection point. 30,000 volts arced through the air. The resulting electromagnetic pulse fried 23 control systems. Total damage $8.2 million. Repair time 11 months. The machine that cost $60 million to build required $8.2 million to fix from one incident. And this wasn't sabotage or operator error. This was geological reality, defeating engineering ambition. During the repairs, engineers discovered something worse. The structural stress analysis showed that Bagger 293's boom, the massive arm holding the bucket wheel, had developed 47 microfractures, not from the incident, from normal operation. The machine was literally tearing itself apart through regular use. The solution was expensive and embarrassing. The entire boom structure had to be reinforced with additional steel plating. Added weight, 380 tons. Added cost, $3.7 million. Bagger 293 had been operating for 6 years. It would eventually run for 20-plus years. But the 2001 incident revealed the truth. Machines at this scale exist at the edge of material science. They're not conquering physics, they're negotiating with it.
The human element. Meet Klaus Zimmermann. He's been operating Bagger 293 for 14 years. His shift starts at 6 a.m. He climbs 96 meters to the control cabin, a 12-minute climb up industrial ladders and stairs. The cabin sits at the top of the superstructure, providing a view of the entire excavation face. Inside, he's surrounded by 34 monitors, 127 switches, and 8 control joysticks. His job sounds simple: operate the machine. In reality, it's like something resembling piloting a building through a minefield. People think I just press buttons and the machine digs, Klaus says. That's wrong. I'm reading ground conditions constantly. I'm monitoring 200 sensors. I'm adjusting the wheel speed, the crawler track angles, the conveyor belt tensions. If I make one mistake, one wrong angle, one miscalculation of ground stability, I can damage equipment worth millions. His salary, $78,000 annually, $84,500 USD. Good money, but consider the responsibility. He's controlling a machine that costs $60 million, consumes 16.56 megawatts continuously, and can remove 240,000 cubic meters of earth daily. The hardest part isn't the technical complexity, it's the isolation. Klaus works alone in that cabin for 8-hour shifts. The nearest human is 200 meters away. The machine's noise, the constant mechanical roar of conveyor belts, hydraulic systems, and the grinding bucket wheel makes radio communication difficult. And there's the psychological weight. Klaus knows that if something goes wrong, if the ground gives way, if the boom structure fails, if the electrical systems arc, he's sitting 96 meters in the air in a metal cabin powered by 30,000 volts. The emergency escape system is a ladder. It takes 12 minutes to reach the ground in optimal conditions. In an emergency, he might not have 12 minutes. I don't think about it, Klaus admits. If I did, I couldn't do the job. The machine requires a crew of 5 operators per shift, 1 in the main cabin, 2 monitoring the conveyor discharge points, 2 managing the external power cable system as the machine moves, plus maintenance crews, 16 technicians per shift performing continuous inspections, lubrication, and minor repairs. Total personnel to operate Bagger 293, 37 people per day, across 3 shifts, 111 people. The machine requires a workforce the size of a small factory just to function. The economics of absurdity. Here's where the numbers become genuinely shocking.
Purchase price $1995, $60 million. Annual operating cost $114.7 million. That breaks down to electricity, $8.9 million annually. Maintenance, $3.8 million annually. Replacement parts, repairs, inspections. Personnel, $2 million annually. 111 workers, tax average salary. Over its 25-year operational life, $367.5 million in operating costs. The machine that cost $60 million to build costs 6 times that amount to operate. But here's the shocking part, it's still economically viable. Why? Because the alternative is of course even worse. To match Bagger 293's output using conventional excavators, RWE would need approximately 40 large hydraulic excavators operating simultaneously. Each excavator costs $800,000. Total, $32 million in equipment. But the real cost is personnel. Each excavator requires 3 operators per day, 3 shifts. 40 excavators tax 3 operators, 120 operators. At an average salary of $65,000, that's $7.8 million annually, just for operators. Plus 40 machines consuming diesel fuel, requiring maintenance, needing replacement every 8 to 10 years. The total cost would exceed $500 million over 25 years. Bagger 293, despite its absurd operating cost, saves RWE approximately $132 million over its operational lifetime compared to conventional alternatives. The economics work, barely, but they only work at scale. If production drops below 180,000 cubic meters daily, the machine becomes economically unsustainable. It's too expensive to run at partial capacity. This creates a perverse incentive. Once you build a machine like Bagger 293, you must keep mining. You can't slow down. You can't stop. The machine's economics demand continuous operation at maximum capacity. Germany veers America, the bucket wheel divide. The United States has massive open-pit mines, copper mines in Arizona, coal mines in Wyoming, iron ore operations in Minnesota. But America never built bucket wheel excavators on this scale. Why? The answer reveals fundamentally different engineering philosophies. German approach: build one enormous machine, centralize operations, maximize efficiency through scale, accept the risks. American approach: build many smaller machines, distribute operations, maintain flexibility, minimize single points of failure. American mines use drag lines, massive excavators with cables and buckets that can move 100 to 150 cubic meters per cycle, or hydraulic excavators in large fleets, or truck and shovel operations where loaders fill 400-ton haul trucks. The largest American mining excavator is the Bucyrus RH400, weight 980 tons, 14 times smaller than Bagger 293. Capacity, 45 cubic meters per cycle, 20 times less than Bagger 293's continuous output. But here's what American engineers understood. If one RH400 breaks down, you have 19 others operating. If Bagger 293 breaks down, the entire mine stops. The 2001 incident proved this. When Bagger 293 sank and required 11 months of repairs, RWE's production dropped by 42%. They had to contract external excavation companies to maintain coal deliveries. Cost $23 million. American mines don't face this vulnerability. Distributed systems are resilient. Centralized systems are efficient but fragile. Neither approach is wrong. They're optimizing for different priorities. Germany, maximum efficiency in stable geological conditions. America, maximum reliability in variable geological conditions. The irony is that both countries are now phasing out coal mining entirely. Germany is closing lignite mines by 2038. America's coal production has dropped 60% since 2008. The machines built to maximize coal extraction are becoming monuments to an industry in terminal decline. 2035, the death of giants. Bagger 293 will likely be decommissioned between 2026 to tyranny. What happens to a 14,200-ton machine that can't be easily moved or disassembled? RWE has 3 options, each absurd in its own way. Option 1, bury it. When the Hambach mine closes, fill the excavation with water, creating an artificial lake, and leave Bagger 293 at the bottom. Cost, environmental impact, questionable. Public relations, terrible. Option 2, disassemble it. Cut the machine into transportable pieces, sell the steel for scrap. Revenue, approximately $8.5 million, 14,200 tons checks price. Cost to disassemble, 12R $18 million. Net loss, $3.59.5 million. Option 3, preserve it. Convert it into an industrial monument/museum. Maintain it as a tourist attraction. Estimated annual maintenance, $400,000. Potential tourism revenue, unknown. Early indications suggest RWE is considering option 3. The machine is already somewhat famous. It appeared in music videos, documentaries, and even video games. There's cultural value in preserving the largest land vehicle ever built. But here's the bigger question. Will machines like Bagger 293 ever be built again? The answer is almost certainly no. Modern mining is moving toward automation, electrification of truck fleets, and AI-optimized extraction. The future isn't one giant machine. It's 100 autonomous haul trucks coordinated by artificial intelligence. It's electric excavators powered by renewable energy. It's drones surveying optimal dig patterns. The engineering philosophy that produced Bagger 293, centralization, maximization, mechanical dominance, is being replaced by distribution, optimization, and digital intelligence. Bagger 293 represents the peak of 20th century industrial thinking. Bigger is better. Scale conquers all. If the machine is large enough, it can reshape landscapes. But 21st century mining has learned the lessons of the 2001 incident. Scale creates vulnerability. Centralization creates risk. The largest machine is impressive, but 100 smaller machines, working in coordinated networks, are more efficient, more reliable, and more adaptable. The age of mechanical giants is ending, not because we can't build them, but because we've learned we shouldn't. The final question. Bagger 293 removes 240,000 cubic meters of earth daily, operates 20+ hours per day, consumes enough electricity to power 17,000 homes, costs $14.7 million annually to run, all to extract low-grade coal that's being phased out globally. The machine works, the engineering is sound, the economics barely make sense, but here's the question nobody asks. Just because we can build a machine this large, this powerful, this dominant, does that mean we should? Bagger 293 will outlive the industry it was built to serve. It will become a monument to human ambition, engineering capability, and the limits of both. What do you think is more important, building the largest machine possible, or building the right-sized machine for a sustainable future?